Okay. In this video, we're going to focus on how to make carboxylic acids. Before looking at new methods, let's just review the old methods that we already know. Way back in the aromaticity chapter, we saw that you could take an alkyl side chain on a benzene ring like this, and as long as you have a benzylic hydrogen, okay, like we do here, as long as you got one of those, at least one, and you treat this with either potassium permanganate or chromium trioxide, or sorry, dichromate species, you'll totally oxidize the chain to the carboxylic acid group. Yes, indeed. If you look at the equation, yes, a carbon-carbon bond does break. As long as you've got that one benzylic hydrogen right there, that's going to start everything, and you're going to break the bond between carbon and R. Okay, so that bond is going to get broken as a result of that reaction. Okay, we also learned that if you take primary alcohols, like right here, and we treat it with an aqueous chromium-6 source like chromic acid or sodium dichromate in an aqueous system, we won't oxidize to the aldehyde, we'll oxidize all the way to the carboxylic acid. Okay? All right, and finally we can take aldehydes and do this one-step oxidation of the aldehyde to the carboxylic acid. I should note here that this compound, the aldehyde, is an intermediate in this reaction right here. Okay, it's just that it doesn't stop at the aldehyde stage, and there are more selective reagents that you can use, like Tollen's reagent, that are very selective for just oxidizing aldehydes in the presence of alcohol functional groups. Okay. All right, so let's look at some new methods that we're going to introduce in this chapter. And we're going to introduce two methods. One is a Grignard-based method. If we take a Grignard reagent or an organolithium reagent and we treat it with carbon dioxide, we're going to get a carboxylate salt, a magnesium carboxylate salt. And if you work this solution up with some acid, what you'll do is you'll protonate the carboxylate salt and you'll get the carboxylic acid. You can't just add water here because the carboxylate salt is not basic enough to pull the proton off water. You actually have to add something quite acidic that'll get the pH down to something, we say generally below 4, but it has to go below the pKa of the carboxylic acid that you're making. All right, so here's an example of the equation. Here we have isobutyl Grignard. It's reacting with carbon dioxide, and after we acidify it, this is just a way we express what we're doing here to work this up so as to get the free acid. We're going to get this 5-carbon acid. Okay, and how does this work? Well, look right here. We have a carbon-oxygen double bond, and we've seen how nucleophiles add to carbon-oxygen double bonds quite extensively in the previous few chapters, right? And the CO2 is just another carbon-oxygen double bond as far as this equation here goes. Okay, for now we're going to continue to use this analogy that the Grignard reagent or the organolithium reagent is equivalent to just the free carbanion. We're going to find a little later in a couple of chapters, or in the next chapter, one system where that analogy doesn't really work that well, but for now it holds quite well. All right, an important point to note here is that the product has 5 carbons. The starting material has 4 carbons. The CO2 is a source of 1 carbon. So your product will have 1 more carbon than your starting material when you use this method. It's important to remember that, because when you look at this method here that we looked at in the previous slide, the number of carbons does not change. Okay, so that's one way to tell which of these methods you might want to use by looking at whether whether the carbon count is the same on the product and reactant side of the equation. All right, the only limitation of this reaction here is really the limitation of the Grignard reagent. If we can make the Grignard reagent, we can normally treat it with CO2 to convert the Grignard reagent to the carboxylic acid. So the limitation is if you can't make the Grignard reagent, you can't do this reaction. But if the Grignard reagent is of the type that you can make it, this reaction should work just fine. All right, the other method we're going to introduce also has this feature that it adds a carbon. And this is an SN2 based method. Okay, so we're going to take either an alkyl halide or an alkyl tosylate, and we're going to do an SN2 reaction with sodium cyanide. And that's a reaction that we saw quite exhaustively in the SN2 chapter. This, of course, does make a nitrile. And a nitrile, it turns out that you can perform a hydrolysis reaction. You can either use acid, H3O plus heat, or you can use base. If you use base, you're going to have to acidify it to turn the carboxylate salt into the free acid. But either of these methods can turn the nitrile into the carboxylic acid. Okay? All right. This method, also note that it increases the carbon count by 1. We're not going to present the mechanism here for this hydrolysis reaction because it involves amides, and we're going to talk about amides in the next chapter, and it's most convenient to present this mechanism and the hydrolysis mechanism for amides at the same time. All right, so if we take this species here, notice that it has 5 carbons. We're going to carry it through the cyanide followed by hydrolysis. We get a carboxylic acid that has 6 carbons. Our limitation here is the limitation of the SN2 reaction. As long as we have an alkyl halide or tosylate that's capable of doing the SN2 reaction, this reaction should normally work. And again, one thing that's common to both of these reactions on this slide here is that they increase the number of carbons by 1, whereas the oxidation method in the previous chapter does not do anything, does not change the number of carbons. All right, we're going to stop this video here by looking at one synthesis problem. Okay, and this is going to merge some ideas from the ketone and aldehyde chapter with some of the features here. So let's devise a sequence of reactions that are going to carry out the following transformation. And note here that one of the things that's of course happening is that we are increasing the number of carbons in the system. So this tells us to use either the Grignard followed by CO2 route or use the cyanide followed by hydrolysis route. But it looks like we got problems. We can't make the Grignard reagent from this compound because it's got an aldehyde in it. Okay? Yeah. So a Grignard reagent like this could never have any sort of lifetime because of the incompatibility of that functional group with that functional group. All right? Okay, so we can't use the Grignard. What about the cyanide route? Well, it looks like we can't use that one either because we can't do an SN2 reaction at this type of halide. This bromine is attached to a sp2 carbon, and we don't really have a ring that's loaded with nitro group, so we can't really do a nucleophilic aromatic substitution here very effectively. So is this an undoable problem? Well, actually, no. This is a prime example of a place where we can use protecting groups to solve a very difficult synthesis problem. Okay, so we're going to use the acetal protecting group. So our final step in this is going to be hydrolysis of the acetal group right here to turn the acetal into a carbonyl group. Okay, so remember that we can make Grignards in the same molecule as an acetal, because an acetal is an ether, and ethers do not react with Grignard reagents. All right, so what we would do is we would take this compound now, and we would make the Grignard reagent from this compound, and step 1 there gives us this compound, and we don't have any problem at this point, right? Okay, so we can make that Grignard, and then step 2 would transform it into that. All right, so all we need to do in the first step is turn the aldehyde group into the acetal group. Okay? All right, and let's see. Let me just... yeah, so let's just turn the... yeah, so all we have to do is turn the aldehyde group into the acetal group using ethylene glycol in this case, or you could have used methanol or something like that. I just used this one because this is one of the easier ones to work with. All right, so this is where I'm going to stop this video. In the next video, we're going to look at reactions of carboxylic acids. Okay?